This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on marginal analysis. And here's our basic idea, and this works for cost, revenue, or profit, is the derivative of that function is approximately the difference in cost of the x plus first element and the xth element. So what is the additional cost you need to incur to make one more item? That's in essence what the marginal cost represents. And again, same thing for revenue or for profit. So R prime of x would be the additional revenue you get for selling one more product. So C of 57 is the total cost of manufacturing 57 items. So if you want to determine what will it cost us to manufacture 57 items, that's plugging 57 into the cost function. But C prime of 57 is the additional cost to make one more. We've made 57 to make one more to make the 58th item. How much more are we going to have to spend? That's the idea of the marginal cost function. So here's an example for us. We have the total cost of producing X bicycles is that function, and find the cost of producing the 121st bicycle. Now, to get an exact value, we would take the cost of the 121st and the cost of the 120th and subtract them. So plugging in 121 into the cost function, 10,000 plus 150 times 121 minus 0.2 times 121 squared, we get 25,221.8. Total cost of producing 121 bicycles. We have to do the same thing for 120, plugging in 120 for x, 10,000 plus 150 times 120 minus 0.2 times 120 squared, and that is 25,120. So the difference of these two would be the cost of producing the 121st. So the total cost of 121 is here, the total cost of 120. The additional cost to produce the 121st bicycle would be 25,221.8 minus 25,120. Now that answer is $101.80. That is the exact cost of producing the 121st bicycle. But the derivative can give us a relatively good approximation as long as this difference of 1 is relatively small compared to the other numbers. So how do we do that? We have our cost function here, 10,000 plus 150x minus 0.2 times x squared. Taking the derivative, that's 150 minus 0.4x. What we're doing is we're going to plug in 120 into that derivative function. So we get 150 minus 0.4 times 120, which gives us $102. That is the approximate cost of producing the 121st bicycle. And as we saw on the previous slide, the actual cost is $101.80. So $101.80 compared to $102, you can see those are very, very close. So the marginal cost, again, if that 1 is relatively small compared to the other numbers at hand, the approximation from the marginal cost, revenue, profit should be very similar to the exact that we're going to get. Now let's take a look at that. There it is again. Let's look at the marginal as a differential. So I have this cost function is 10,000 plus 150x minus 0.2x squared. And there's our derivative, 150 minus 0.4x. We know that dc dx is c prime of x. So dc is c prime of x dx from our differential idea. And then the change in cost is approximately the derivative times the change in x. So the change in cost here would be 150 minus 0.4x times change in x. X is 120. We started making 120 bicycles. We want to make 121. The change in x is 1. If you're using this marginal approach as a differential, that change in x is always 1. But you can see we get the same answer, that our change in c is 102, that the additional cost incurred by manufacturing the 121st bicycle is an additional $102. So in essence, the marginal approach is equivalent to the differential when the change is always just equal to 1. So it's a special case of a differential. Let's take a look at another problem here. The price-demand equation is 10,000 minus 1,000p. X is the total demand for a certain price P. We want to find the marginal revenue at x equals 2,000 and interpret its meaning. Well, revenue is the number of items we sell times the price per item. So I need to solve this for P. I need to find out what the price per item is. So starting with x equals 10,000 minus 1,000p, x plus 1,000 p is 10,000. Solving for p, subtracting x from both sides. 1,000 p is 10,000 divided by x. Then divide both sides by 1,000. And I have 10,000 over 1,000, which is 10 minus x over 1,000. So that when we reduce that fraction, we get the price as a function of demand is 10 minus x over 1,000. So knowing that, what are we going to get? We have to recognize that revenue is, again, x, number of items we sell, or our demand, times p, price per item. So if revenue was x times p, where does that leave us? We get x times quantity 10 minus x over 1,000. Multiplying in that x, it'll be 10x minus x squared over 1,000 is our revenue function. Now we want to find the marginal revenue at 2,000. To find the marginal, we're going to have to take a derivative of this revenue function. So the derivative of 10x minus the derivative of x squared over 1,000. Derivative of 10x is 10. Pull out the 1 over 1,000. Derivative of x squared is 2x. So the derivative of the revenue function is 10 minus 2x over 1,000, which of course becomes 10 minus x over 500. 2 over 1,000 is 1 over 500. But I want the marginal revenue at 2,000. It'll be r prime of 2,000. So it's 10 minus 2,000 over 500, or 10 minus 4. 6. So if we're going to sell the 2,000 first item, we will get an additional revenue of $6. That's what that means. So I guess I need to change that because we're focused on revenue, not on cost. Let me fix that. Additional revenue gained by producing and selling the 2,000 first item is $6. Since our interest here was revenue, the revenue changes by $6 if we produce and sell the 2,000 first item, one more than the 2,000 we started with. Let's take a look at one more example. Total cost of producing X food processors is that. The exact cost of producing the 21st would be the cost of 21 minus the cost of 20. So the cost of 21 requires us to plug in a 21 for X here, a 21 for X here. So the cost of 21 is 2,000 plus 50 times 21 minus a half times 21 squared, which is $2,829.50. The cost of 20, we'll plug in 20 for both of those x's up there. So the cost of 20 is 2,000 plus 50 times 20 minus a half times 20 squared. So the additional cost of producing the 21st is the difference of those two. So C21 minus C20 would give us $29.50. That is the cost of producing the 21st item. We can also approximate that by looking at the marginal approach. So I want the marginal cost to approximate that cost of producing the 21st food processor. We have our exact cost. Our exact cost is $29.50. To approximate this with the marginal, we're going to take a derivative. So the derivative of C will be C prime of X. So C of X is 2,000 plus 50X minus a half X squared. C prime of X, the derivative of 50X is 50. The derivative of a half X squared is a half times 2X, or 1X. So C prime of X is 50 minus 1X. I want to approximate the cost of producing the 21st food processor. That will be C prime of 20. So I plug 20 into our C prime function. So that is 50 minus 1 times 20. So we get C prime of 20 is 30. So what that tells us then, the approximate cost of producing the 21st food processor, one more food processor beyond 20 is an additional $30. And that will conclude this lesson.